Hello viewers, today we are going to discuss what is known as magnetostatics. Here in this chapter we will be discussing about what is the magnetic field strength capital B bar, H bar and intensity of magnetization capital M bar, how a charged particle moves in an external magnetic field, okay, what is current due to, what the magnetic field due to a current wire, okay, various different types of segments of current wires, what type of magnetic fields they produce, and Biot-Savart law, okay, Ampere circuit law, etc. These are the topics which will be covered under the section called magnetostatics. Okay, here I am going to define what is known as the first important magnetic field vector is B bar. It is called magnetic. It is called magnetic field strength. It is called magnetic field strength or magnetic flux density also. Magnetic flux density or magnetic induction. Okay, we can call B as many names. Magnetic field strength or flux density is commonly used for magnetic induction also. Okay, its units are Weber per meter square or Tesla. Its units are Weber per meter square or Tesla. This Tesla is a very large unit of magnetic field. Okay, so how much? 1 Tesla equal to 10,000 Gauss. 1 Tesla equal to 10,000 Gauss, 10 to the power 4 Gauss we write. Okay, Tesla is a very big unit of magnetic field. Tesla is a very big unit of magnetic field. Okay, now how do we define B? B is the number of magnetic lines of force passing through unit area. Okay, unit normal area is like this. How many number of lines of force are passing through this area? That is defined as magnetic flux density or magnetic field strength or magnetic field strength. Okay, right? B is number of lines of force passing through a unit cross-sectional area which is normal to the direction of B. Okay, so B units are Weber per meter square or Tesla we have seen. Now suppose say a bigger area is there. Okay, bigger area per unit area, number of lines of force passing through are B. Suppose say 20 lines of force are passing through a square centimeter. So what is B? B equal to 20 units I will say. Now if the area is bigger, okay, suppose say 15 centimeter square area is there. How many number of lines of force are passing through the entire area? Okay, that is total number of lines of force passing through any given area. It is called magnetic flux phi B. Okay, magnetic flux phi B. So per unit area of B number of lines of force are passing, the total number of lines of force passing through any given area will be phi B is called magnetic flux. It is right B into area we write. B into area or surface area, we can take it as S. B into S I'll write. Okay, this is surface area, number of lines of force passing through unit area into total area will give you total number of lines of force passing through the entire given area, that is known as magnetic flux phi B. Its units are Weber. Its units are Weber. Weber per meter square into meter square. Its units are Weber or Tesla meter square we write. Okay, Tesla meter square. Okay, now phi B is magnetic flux. Phi B is magnetic flux. Now suppose say how much is phi B means B into area I am saying. Okay, let us see that now. Suppose say in this room there is a uniform magnetic field of intensity of strength B which is vertically upwards. The number of lines of force passing through 1 square centimeter, suppose say 20. Okay, if I put my hand, my palm itself I am putting here, per square centimeter of my palm 20 lines of force are passing through, so B equal to 20 units. The total number of lines of force passing through my entire palm is how much? Means B into 20 into area of my palm. That will give you magnetic flux through my palm. Okay, if I put my palm like this, okay, the total number of lines of force passing, flux is equal to B into area will give me correct result. But suppose say if I put my hand like this, Okay, my hand like this, B is straightly pointing upwards, my hand is slightly inclined now. Do you expect the number of lines of force passing through my hand to increase or decrease or remain same as before? Obviously, when I am putting a slant area like this, the number of lines of force passing through the slant area will be less than the lines of force passing like this. Okay, so what is happening? B is same, area of the palm is remaining same, but the flux passing through my hand is decreasing. If I still increase the angle like this, still lesser number of lines of force will be passing through my hand. If I put my palm like this, the number of lines of force passing through my palm will be 0. Means here B is remaining constant, area of my palm is also remaining constant, but the flux is found to be maximum when the palm is like this, when the flux is found to be 0 when the palm is like this. Means the number of lines of force, the total number of lines of force depends not only on B value, not only on the area, but also between the orientation of that area and the magnetic field. Okay, means if I simply write it as B into S, that will not give me the correct picture. Okay, I have to include one more parameter here, that is the angle between B and area. The angle between B and area is also important to us. Okay, so I'll express it like this. Okay, now you take, now my palm is like this, I will draw a normal to my palm. Okay, that is pen is normal, okay, normal to my palm. The angle between pen and my hand is always 90 degrees, it is always 90 degrees. Okay, when my palm is like this, maximum number of lines of force are passing through my hand. Okay, the angle between, now forget about my hand now, concentrate on the direction of angle between B and this pen. Pen is perpendicular to my hand, no doubt. Okay, now concentrate on the angle between B and pen. Okay, when my palm is like this, the angle between B is also like this, pen is also like this, the angle between B and pen is 0. Cos 0 is maximum 1. Okay, flux passing through my palm is also maximum. When I put the palm like this, okay, forget about my palm, the angle between B and the pen is 90 degrees, cos 90 is 0, flux passing through my hand is also 0. Means the cosine of the angle between the pen and the magnetic field should also be considered. If that cosine is becoming maximum, flux is becoming maximum, cosine 0, flux 0. That is, okay, right, the correct description of what you call magnetic flux will be, right, B into surface area into the cosine of the angle between the pen and the magnetic field. Okay, that is theta is, right, the angle between B and S. So Bs cos theta, I'll write phi b as equal to B bar dot S bar. I'll write this is nothing but B S cos theta, but S bar is area. Area is in general not a vector, it has only magnitude. So what do? I'll convert that scalar area into what you call a vector by assigning some direction to it. What is the direction assigned to the area? Okay, it is always normal to the area. If the area is like this, I will draw one normal n cap like this. Okay, right, this is normal n cap is S bar equal to, right, S into n cap. Means the vector S bar has magnitude S, its area is S, and what is its direction? Normal, outward drawn normal to the surface, we say. Outward drawn normal to the surface. So B bar dot S bar equal to S into n. So what is flux phi b? Phi b equal to Bs cos theta. Okay, right. Now the small amount of flux passing through a small area ds, I'll write this like this, B bar dot ds bar. Okay, d phi b is the small amount of magnetic flux passing through a small area ds bar, B bar dot ds bar. Okay, now what is the total amount of flux passing through the entire area? Means I'll integrate it. Flux passing through any given area, right, is integral d phi b equal to integral B bar dot ds bar. Integral B bar dot ds bar is the total flux passing through given area. Okay, integrate under the area limits. Okay, another way of defining B also. Okay, how do we define B bar? Means I'll take some point P. Okay, I'll fire a test charge Q with a velocity v through that point P. Okay, I'll take some charge q, right, and I'll shoot it through some velocity v through some point p. Okay, if that charged particle experiences a sideways reflecting force means what? If the particle is going in a straight line like this, it should get sideways reflecting force means it should get deflected either towards left or right or towards up or down, towards up and like this. Okay, if it gets deflected from its linear path, that is called sideways deflecting force. If it experiences sideways deflecting force, okay, satisfying the condition F bar equal to Q into V bar cross B bar, then there exists a magnetic field of induction B, we say. Okay, means look at this definition, it's a slightly roundabout definition. Okay, I'm not saying whether B is there or not. Okay, how am I defining the amount of B there? Okay, we have to take one charge q, okay, shoot it with some velocity v. Okay, if that particle experiences a sideways deflecting force, okay, satisfying this condition F equal to Q into V cross B, then we say there exists one magnetic field of induction B. Okay, right? This is slightly roundabout rule. Now, roundabout definition. So this force is also known as Lorenz force. This force is also known as Lorenz force. F bar equal to Q into V bar cross B bar. Okay, this is with the magnitude and direction. What is the magnitude of that force F bar? F bar equal to QVB sine theta, we write. Okay, F bar equal to QVB sine theta. Okay, right now, what is the means F bar will be, what is the direction of F bar? This is very, very crucial now. Okay, what is the direction of F bar? F bar is perpendicular to both V and B. Resultant of cross product of two vectors is always perpendicular to both the vectors, or perpendicular to the plane containing those two vectors, we say. Okay, so look at this, V bar cross B bar. Suppose say velocity is in this direction, B is like this. B is like this. So what is the cross product of V bar and B bar? Okay, the angle between them is theta. How do we take the direction? V cross B means close your right hand fingers from V to B. Close your right hand fingers from V to B, right? The thumb will give you the direction of the external magnetic field. Okay, if you close your right hand four fingers from V to B like this, okay, thumb will give you direction of the magnetic field, means direction of the resultant. Okay, that is the resultant, whatever is resultant of V and B, here of course it is force. Okay, it will be pointing out of the board like this. Okay, now I'll get it out here. Okay, how to close my right hand finger? See, it is my fingers only. Okay, I close your right hand fingers from V to B means I can close like this or like this. I can close. Both are V and B only. Okay, then which way to close? Some people think that it is smaller angle, but it is clockwise, anti-clockwise. No. Okay, it is the smaller angle between them. Okay, whichever direction, if you rotate your fingers, right, the direction is smaller. Through in that direction you have to close your right hand four fingers. Okay, so this is a smaller angle between them. Suppose if V is like this, okay, B is like this. Okay, how to close your right hand four fingers? Okay, like this. Okay, then also the resultant will be pointing out of the board. Okay, if V is like this, okay, B is like this, then right, the smaller angle will be like this. If you close your right hand four fingers from V to B, thumb will be pointing into the board, the resultant will be pointing into the board. Okay, right? Now, so the resultant of cross product of two vectors is always perpendicular to both the vectors or plane containing V and B. It is perpendicular to the entire plane of V and B. Now V and B in this example are in the plane of the board, so resultant will be perpendicular to the board. Okay, into the board or out of the board. Perpendicular means you have to find out using this right hand screw rule. Okay, close your right hand fingers from V to B, thumb will give you direction of the external force. So force is always perpendicular to both V and B. That is the meaning of cross product. Force is perpendicular to velocity means what? Okay, if the particle is moving like this, force is acting some perpendicular direction. Perpendicular direction means it can be like this or it can be like this. In whichever direction that force is acting, the particle will get deflected in that direction. So that's why it is called a sideways deflecting force. Okay, and one more thing, when the force and velocity are perpendicular to each other, work done, okay, will be zero. Work done, how do you write? F bar dot S bar force, F dot displacement. Okay, right? Displacement will be in the direction of the velocity. Means force and displacement and force and velocity dot product it is. If they are perpendicular, resultant will be 0. Resultant will be 0 means what? The magnetic fields will not do any work. When magnetic field is not doing any work, work energy theorem says what? Energy of the particle cannot be changed. Okay, that is, particle's energy will not get changed by the magnetic field. Okay, since magnetic field is always a sideways deflecting force, magnetic fields do not do any work on the particle. That is, they cannot alter the kinetic energy of the particle. They cannot alter the kinetic energy of the particle. Particle continues to move with same speed. Particle continues to move with same speed. Okay, that is one aspect of what you call F equal to Q into V cross B. Other one is now on what conditions this force will act. F equal to QVB sin theta we are saying. Okay, now what are the things that are obvious from this expression? Okay, F is Q is there. Okay, if the particle is not having any charge, Q equal to 0, force will be 0. Means magnetic fields do not act on neutral particles. Magnetic fields do not act on neutral particles. That is first thing. Next one, if the particle is not moving, for a stationary particle, velocity will be equal to 0. Okay, when velocity is 0 also, force will be 0. Means magnetic fields do not act on stationary particles also. Sometimes question will keep coming like this in the exam. Okay, an electron is placed at the center, in the center of a room. Okay, and a uniform magnetic field is acting from east to west. Okay, in which direction the electron moves? Okay, electron will move only when there is some net force acting on it. Okay, right? If what you call magnetic fields do not act on stationary particles. So in the problem, electron is placed at rest at the center of a room. Okay, in which there is a uniform magnetic field acting from east to west or west to south or north to south, something like that. Okay, in which direction the electron moves? Electron does not move because, right, magnetic force comes into picture only on moving particles. Okay, right? Next one, if B is not there, no magnetic force, no problem at all. Okay, so QVB, even when theta equal to either 0 degrees or 180 degrees, theta equal to 0 degrees or 180 degrees means what? If the angle between the velocity and magnetic field is either 0, velocity and magnetic field angle is 0 means what? If B is like this, velocity is also in the direction of V. Okay, velocity is also in the direction of B, then the angle between V and B is 0, right? Force will be equal to sin 0, 0. Or when the particle is moving in opposite direction to the magnetic field also, in this case theta will be equal to 180 degrees. Okay, sin 180 is also 0, F equal to 0. Means when the particle is moving in the direction of the magnetic field or in opposite direction to the magnetic field, that is, if the motion is either parallel to the field or anti-parallel to the field, in that case also magnetic field will not act. Okay, so magnetic field will not act on uncharged particles. Magnetic field will not act on stationary particles. Okay, if there is no field, no force at all. Okay, right? Even Q is there, V is there, B is there. But if the particle is moving in the direction of the magnetic field or in opposite direction of the magnetic field, parallel or anti-parallel also, right? Force becomes 0. Okay, and one more thing. Since F and V are perpendicular to each other, magnetic fields do not alter the kinetic energy of particles. Magnetic fields do not alter the kinetic energy of particles. Okay. Right, these are some points which we have to keep in mind. Now what is the direction of force? Okay, it is cross product of V and B. If V and B are perpendicular, okay, means you suppose say V is like this, okay, in a region, and B is like this. V and B, angle between V and B is 90 degrees. That is, V cross sin 90 is maximum. That maximum force is nothing but QVB, we write. Maximum force is QVB, right? Okay, right? What is the maximum possible force? When V and B are perpendicular, the force will be maximum given by QVB. Okay, in that case, we can use Fleming's left hand rule also. In that case, we can use Fleming's left hand rule. Okay, what does Fleming's left hand rule say? Okay, right? Forefinger in the direction of the field. Forefinger in the direction of the field. Middle finger is the direction of velocity of the particle. Okay, keep all them in their natural directions perpendicular to each other like this. Thumb will give you direction of the force. This is called Fleming's left hand rule. Okay, right? Forefinger will give you direction of the field. Middle finger is the direction of velocity. Okay, then when they are perpendicular like this, spread in their natural directions, right, force will be acting in the direction of thumb. This is called Fleming's left hand rule. Remember, if suppose a field is like this, you should not bend your finger and put like this, and if the velocity is like this, you should not do like this. Okay, they should always be fixed like this only. Okay, only thing is you have to put what you call field and velocity. You have to change what you call, you have to rotate your entire wrist, okay, such that the angle between them will not change. You should not change. Okay, if velocity is like this, force is in this direction, put the entire hand like that. Or if field is in some other direction, put like this. Okay, velocity in some other direction, you have to choose. You have to rotate your entire wrist, but you cannot simply, right, say field is like this, velocity is like this. No. Okay, right? So this is called Fleming's left hand rule. Forefinger, field direction, middle finger, velocity direction, thumb will give you the resultant force. Okay, now some problems keep on coming. That force experienced by a charge q in an electric field, F bar equal to QE bar, we write. Okay, whenever you place a charge q in electric field of intensity E, it experiences a force given by F equal to Q into E bar. This is also Lorenz force only. Okay, now suppose in a region there is an electric field in some direction, there is some magnetic field in some other direction, and you are placing some charge there. If you are putting charge at rest, magnetic field will not work. Okay, if the charge is moving, then both electric and magnetic fields will working. What is the resultant force? Resultant force F bar equal to, right, Q E bar plus Q into, right, V bar cross B bar. This is also Lorenz force only. This is the general Lorenz force. If only electric field is there, F equal to QE. If only magnetic field is there, F equal to Q into V cross B. If both are present, this is the resultant Lorenz force. Okay, now we are discussing about magnetostatics, so let us concentrate only on the relation F equal to Q into V cross B for some time. Okay, right? Now a question, problems keep on coming. There is a uniform magnetic field acting vertically upwards. Okay, B equal to 2 Tesla magnetic field is acting vertically upwards in a region, in a room. Okay, in which an electron is projected with a velocity of, okay, 6 into 10 to the power 6 meters per second. Okay, 6 into 10 to the power 6 meters per second from west to east. From west to east. Okay, right? In which, in a room where there is a uniform magnetic field B equal to 2 Tesla, let us say it is along north, from south to north, say, instead of vertically upwards, let us take it as south to north. Okay, right? What is F bar acting on it? What is F bar acting on it? Okay, question come like this, right? When question comes, right, what do we write? We call F bar equal to mod F bar equal to QVB sine theta. Okay, Q is saying that it is an electron, so charge of the electron we know 1.6 into 10 to the power minus 19 coulombs. Okay, velocity of the electron, that is given 6 into 10 to the power 6 meters per second. Okay, B equal to 2 Tesla magnetic field, he has given uniform magnetic field. Okay, theta means what is the question? Electron is projected from west to east horizontally. Okay, in which there is a uniform magnetic field of induction B from south to north horizontally, means, right, magnetic field is like this, velocity is like this. What is the angle between velocity and magnetic field? 90 degrees. Okay, that is sine 90 equal to 1. Okay, that is mod F bar equal to maximum Q into V into B. So Q value is known, V value is known, B value is known. Substitute and simplify, you will get the magnitude of the force. Okay, now what is the direction? What is the direction means, I told you, when V and B are perpendicular to each other, okay, we can use Fleming's left hand rule. Okay, we can use Fleming's left hand rule such that you should put forefinger in the direction of the field. Okay, forefinger in the direction of the field. Now anything direction can be taken as north. Suppose say I am taking direction towards you as north. Okay, when this is north, the direction that is towards right of the north is east. Okay, and opposite is west, towards my side it is south. Okay, now magnetic field is acting from south to north towards you like this. South to north towards you like this, and electron is moving from west to east like this. So I have to put my forefinger towards you. I have to put the velocity like this. Okay, then the extended thumb will give you the direction of the force. That is, the force when velocity is like this, force is like this. Okay, the force will be field is like this. The force will be acting vertically upwards. Okay, vertically upwards. Okay, right? So the magnitude means F bar, if he is asking, you have to calculate its magnitude, and whatever it is, whatever you get, okay, F into Q, so F equal to Q into V cross B, and direction is vertically upwards. You should write vertically upwards. Okay, vertically upwards you write. Now sometimes, suppose say this is north, okay, east is like this, right? A particle is projected, a proton is projected with some velocity v, right, along the northeast direction, along northeast direction. Okay, means like this. Okay, in which there is a uniform magnetic field acting along what you call northwest direction, say northwest direction. Okay, means velocity is in this direction, right? Field is like this. Then you have to put your fingers like this. Okay, finger is pointing, thumb is pointing outwards. That is, force is again out of the board or vertically upwards, we say. So depending, use this Fleming's left hand rule. It becomes easy to find the direction of the magnetic force. Okay, this is about the Lorenz force acting on a particle. Okay, magnetic force always bends the particle's path. Magnetic field cannot alter the kinetic energy of the particle. What can it do? It can simply change the direction. If a particle is going in some straight line, it won't allow the particle to go in a straight line. It will bend the particle's path either towards right or towards left or towards up or towards down. Okay, next our topic will be circulating charges. Okay, or you can put motion of a charged particle in a magnetic field also. So I'll stop here, okay, in this lecture. We'll continue the remaining topics in the next video to come. Okay, thank you.